All right, I've gone in and I've created, you'll see how I do this next time, but I've created another file in Visual Studio Code, and it has a tiny little function in it that we're going to build out the stuff that uses ifs to test this piece of code as an automated test. Now, this is the way to make it so that when you build pieces of code, you actually know that they work. And by doing this, this is a huge productivity benefit. It doesn't make sense on this little tiny piece of code, but that's intentional because I want a small example that you can say, yeah, this little tiny piece of code, I could know if it works right just by looking at it. I could give it this tiny test, just run it once and go, yeah, it works. Okay? But the point of this isn't the code. The point of this is what we're going to build in the testing. So the first thing we look at is kind of the test that I would run right after I develop some function. Run it once, make certain it compiles, take care of those kind of problems, get past that stuff, run it, go, okay, it produced a result. I don't necessarily know if the result is right because I haven't thought about it yet. But I've gotten to the point where I've made it through the first couple steps. I've written it. I think it's probably right in what I want. And I can run it. Now we're going to start adding on to it. So let's actually run this once. I'm going to use this green arrow because I just want to run the whole thing. And down here in the command line window, you see it says x equals 7. And I look up there and I go, 5. Yeah, 5 plus 2 is 7. It's less than 10. So yeah, that seems like the right thing. Now, I'm actually going to go in here and put in some breakpoints. Okay, and we're actually going to run it in the debugger so that we can take a look at what the values are. And this is the kind of thing that makes, Visual Studio Code shine, is I can sit here and run it and I can say, n did become 5 because it was past 5. And then I can step to the next thing. Over here, this little blue arrow up at the top with a little step and stop, and I can step to the next breakpoint. And okay, and it actually did get to the return, which is what I was expecting. And yeah, it produced the output I'm expecting. So I can add breakpoints. The way you take them off is you click on them again. But I can stop the program in the middle and I can poke into it. And that ability to poke into the program can be really useful in the right kind of context. It doesn't work for some things, but I do use a debugger frequently. And this isn't the only debugger that I use. This is great for Python. There's a debugger if I'm coding in C code called GDB that I use that has some tremendous capabilities. There are a bunch of them out there. But it's an important thing to know, hey, I can go poke into the code and see what it does. And we're going to use that in this because when you're looking through a set of ifs, that's an important thing to look at. Now, if you click on this very first one that looks like 2 documents up here, and we go in here, and this very first one that has a document with a plus allows us to create a new document. I'm going to call this ex2. And you'll see we now have a blank here. These other documents are still up here on the tabs, but we've created a new document here. And this is off the screen, but I'm not going to make you watch me type this in. I've pre-edited these things. And the pre-edited versions are checked in with the notes, so that if you want them, you can go get them and run them yourself. We will just paste that in. And here's the things to note. The first thing I did is I created a comment to say what ex1 does. The comment is for the human beings. And it is an important step in your long-term building the code, because I don't care who you are, how smart you are, how good your memory is, unless you have an absolute eidetic memory and you never forget anything, someday you're going to come back and have to edit your own code. And it's going to be in the future and you're going to be going, what does this do? That's you. And somebody else is going to have to look at your code and they want an explanation of what does this do? And generally speaking, my normal thing is if I have a function, a def, a piece of code that's some reusable component that can be called, I put in a comment. And that comment always starts with the name of the function And so it's going to read ex1 takes the numeric parameter n. Okay, I see a numeric parameter. And if it is less than 11, adds 2. Okay. Otherwise, it returns 55. Now, I as a human being can read that and go, I sort of understand what it does. Next, I'm going to go look at the code and read it. But this gives me an edge up on this is what's going on here. All right. Now, at this point, I want to run some examples and test some of the values that it's going to use. And this still isn't an automated test because it relies on the human being reading the output and understanding it. But we've got two different outputs here. And let's put a breakpoint right there. And let's put one right there. And let's walk through it. Let's run it a couple times and see if we get to those breakpoints. So back to the third one down is the triangle with the thing. So we bring up the debugger for Python. And now I'm going to click the green arrow on the left. And yes, I ran to that first breakpoint. So we got to the n+2 case. And I'll explain to you why I put the breakpoints where I did and what I'm looking for. Okay. Yeah, n is 5. This is good. Let's single step through this. Go to the next breakpoint. And yeah, we got to the 55 case and we'll run it to the end and we got the output. So we've been through both sides of our code. Now, when I go and test like this, and there are automated tools for doing this, this is not one of them, but you can still do this with a debugger. You can go and set up breakpoints to make certain you go through every piece of code in your program. Okay, this is called coverage testing, and you want to make certain that you cover everything. There are limits to coverage testing. In a complex program, there are things that you should never reach. For instance, you've got a bunch of stuff and you think you've taken care of every possible case, but there's the possibility in the code, not necessarily in the data, but the possibility in the code of getting to this supposedly unreachable code. You don't have to cover the unreachable code. It is there to catch the impossible, and sometimes you have that kind of thing. But as you verify that you have test cases that are covering everything in your code, one of those things you want to go is, have I gotten all the test cases? Are my set of values correct? Do I have things I've left out? Did I fail to go down this entire branch of the code and never test it? And so you can glean some information from making certain that you've covered all the code. So coverage testing is good. It turns out that in most cases, coverage testing that checks, and this is when you're actually using a coverage testing tool that checks about 90% of the code, is kind of the drop-off point. I mean, if you've covered 85%, you're pretty close. If you've covered 92%, you are definitely there on most programs. 100%, you're wasting time doing coverage testing because you've reached the point of diminishing returns in that coverage testing. So let's break down testing in terms of what it will do and what it won't. And Microsoft, many years ago, it's been a couple decades, produced a set of studies where they said, okay, here's how you deliver software and what you get from the different stages. Coverage testing will find about 20% of the defects in code. That's not very good. Unit testing will bring that up to about 30%. I think their study said 29%. And there's a big overlap between coverage and unit testing. Quality assurance brings this up to about 30%. So if you're in a team and you build software and you've got a separate testing team, a QA team, and they go out there and test stuff, they're going to get you to about 30%. Now, here's the kicker. If your team takes the software and they put together a formal review process where everybody produces software and then it goes to a group of people that goes and reads it, developers, thoroughly, line by line, and goes and reads it and asks questions. Did we meet the criteria? Did we do the documentation and comments? Are the comments readable? Did we leave out anything? Did we do this? Did we do that? What does this code do? How does it work? And those people not just read it, but they take it and they test it so that they understand it, and then they do this thing called a code review, where you get together and you go through everything step by step. That will catch 69% of defects. And the reason why code review catches more defects than anything else is because code review finds things that you left out. When you go and build tests, normally your tests only test what is there, not what you didn't think of. Whereas code review is another set of eyes to say, well, you didn't think of this case, or you left this piece out. And those are some of the most common defects in software. So the ability to read and analyze the code and do code review is really critical. And in this class, we're so far all working independently. The only person reviewing your code is me, and I'm just grading it. I'm not giving you a formal code review. But I think before the end of the semester, we will actually give a pass at working through a code review and see, so you can see how it needs to work. I'm hoping to do that at least. Now, in this case, I see that we went through both of these, so we did a coverage test. And we've got some examples of running it now. So the next thing to do is to automate this test. And we've got some values and we know what we are expecting for results. So let's create another file and automate this. So back to over here to the files. And when I bring the mouse cursor over, we get that little one. And let's do ex3. And let me cut and paste in my first automated test for this. So you'll notice the first thing is, and this is a common thing, I think I've said this before, suddenly there is more test code than there is code in the function. And that's not uncommon. It's important that your test code stay simple. It's no fun to have to test your test code. I think I said that before too, but I'm going to say it again. You're going to hear that one from me. And you'll notice that I've added that this is the automated test version 1. We've got an automated test. And there are some problems with this automated test, but we'll get to those. Let's take a look at what it does first. Okay. I've put in some values, -1, 1, 10, and 20, that I'm pretty certain cover the range of possibilities of input for this function. And I've figured those out by hand. Like, okay, for this function, if I test these values, I should have covered what this function does. So I've already done some analysis to say this set of tests will verify every feature of this function. So at a certain level, I'm looking at the function, I'm saying, what does it do? What kind of input values? How does it map to those output values? And have I covered every possibility, everything in the range of the function to make certain that I have an example of the domain of the function? And remember, in algebra, range is the input, the x values, and domain is the y-put, the output values. So I have looked at this as a pure mathematical problem of, in the range to the domain, do I have an example of everything in its behavior? And in any one of these functions, anytime you can build software that fits this criteria of being a function, and the function doesn't store data, it doesn't keep things around, it's got a set of inputs, it produces a set of outputs. Those are the easiest to debug and get to work functions. Okay? Anything that doesn't maintain any internal information and say, oh, I held on to this value and kept it. Now, there are entire programming languages that are built that way. Python is not one of them. But if you can build functions that way, you save yourself a huge amount of hassle in testing. And writing your code is 5% of the work. 95% is fixing the defects. So when you can go down a path that leads to easier defect fixing, that's the path you want to go as much of the time as you can. So build things that are functional. Now, I did mention that it doesn't work for everything. Good heavens, do you want to have to type in your name and address and date of birth every single time you log into the University of Wyoming's web pages? so that you can re-register for university? No, persistence and state is an important thing that people keep. But whenever you have that, like a database or a thing that keeps your old email, that makes that much more difficult to test. So as much of the code that you can get to be pure functional is good before you get to the part that's hard to test. You eliminate a whole bunch of problems. Now, I haven't changed the function. It does the same thing. All the new stuff is down here at the bottom, where I say I'm going to run it with 1, and then I'm going to do this test. And you'll notice that this is a not equals, is what that is. Right there, exclamation equals. I say if x is not equal to what I expect for the return value. Okay, let's look at what the actual tests are. Let's look at that first one. I'm going to call the function. And you've seen this kind of a thing before where we call a function. And I'm going to pass it a -1. And then I'm going to have the piece of test code down here underneath. But let's look at what happens inside the function. If I call it with a -1, then n becomes -1. N -1 is less than 10. Yes, that is true. That's how an if works, which means it's going to do the kind of code right after it and the block of code right after it until it gets to either a less indent or an else. Okay, so we're expecting it to run line 6. And -1 plus 2 is, let's see, -1, 1, or 0, 1. So I'm expecting to get back a 1. So down here I put together an if that gives me the expected value. And I say if my return value, x, is not equal to, exclamation equals is not equal to 1, what I expect. So I'm going to say, if I got back something I didn't expect to get, then I'm going to print out that the program failed. It didn't work. And my tests generally fall into this category. I'm going to set something up. I'm going to have an expected value. I'm going to run the routine. Then I'm going to say, did I get back what I expected? If I didn't, then there's something broken in the code. If I got back what I expected, I'm happy and I go on to the next test. Now, sometimes you want tests that if it returns this broken value, you just stop the test. Sometimes you want something a little bit more complicated, and I'll show you that in a minute, because there is a problem in this testing code. And, it's not a horrible problem, but there is a problem. And we'll see that and what the cure for it is. Now, immediately one of those questions that you should ask is, we can run the test, we can see it pass, but is the testing code right? And that's one of the reasons you want to keep the testing code as simple as possible so you avoid as many errors in it as possible. So let's look at some of the other test cases and see if we've got everything that we should have in this set of tests. Okay. The next test passes a 1. Well, 1 is going to be less than 10, so it should return 3. And we have a test that says if it's not equal to 3, then it failed. And the next one is a boundary condition. And legitimately, in most tests, you should test everything at every boundary condition in your functions. So here's a boundary condition. I pass in 10. 10 is less than or equal to 10, so it should give me back 12. A more thorough test, I would also pass in 11. And I would say, okay, at 11, does it give me back 55? That test seems to be missing here. But I go on to another test that's 20, and I say if I don't get 55, it failed. And if it goes past all of these, and then I print out pass. The test passed. I'm happy. It worked. So let's run this. And I'm actually just going to use the green arrow over here and run it once. Okay, and by golly, it prints out pass. Okay, now let's see what happens if we make it return a wrong value. Now, if you have a broken clock, the broken clock is right, in the United States twice a day, and most other countries that work on a 24-hour system once a day. So let's just return minus 555555. Right there at the top. And that value is right for some input, but it isn't in my test cases. So I've broken the function, and now I'm going to test the testing code. and let's run it and see what it does. Well, it failed, it failed, it failed, it failed, and then it printed out pass. And that's not really the desirable effect. I would like it to say not only that it failed, but where it failed and why. And if it fails, I don't want it to print out pass. So I'm going to have to build in some additional logic into this to make it work better. But when I start seeing things that say that they failed, I go, okay, something's wrong. And in this case, intentionally something is wrong. But quite often, and I would say almost universally, when I build test code, I will go to the beginnings of my routines that I'm testing, and I will put in values that I know make the test code produce failures, so that I can get some, okay, I built the routine, I did some preliminary testing. I made certain that I've got an understanding of what I've got to build for the test to do coverage. Then I'm going to go build some automated tests based on those ideas. I'm going to run those tests. I'm going to see to it that my routine works. Then I'm going to flip it upside down. I'm going to break the routines and see that I catch failures, that I haven't done something in the testing code that makes the test not work. Okay? I'm going to look through the tests and say, did I cover all the possibilities in the tests? Or did I leave out boundary conditions? Am I thorough? Okay? Then I'm going to remember to take out the piece that causes it to be broken after I'm certain that the tests are good. And I'm going to want to make certain that the tests produce results that reflect clearly so that a year from now, 5 years from now, 20 years from now, if I run this test again because the code is broken, and I say, okay, what do these tests mean? Which things passed, which things failed? Does it still work in the future? That gives me confidence, at least, that if it's broken, the tests that are there worked, or has something changed outside the code? What do I mean by outside the code? This is running in Python. We're on version 3.8.3 or 3.8.4, depending on the exact day that you installed this. Suppose that we go to a new version in the middle of this semester. We get a 3.8.5, and we all go and install it, and suddenly we're testing something, and it doesn't work anymore. I mean, Python gets a lot of testing before they release a new version, but suppose that they broke it. It's a piece of software. It has defects. Every piece of software has defects. And maybe one of those defects is now affecting us. We want to know, is it our code or is it the Python language? And we've got to be able to have tests that say that. And you go, does this really happen? Yeah, this really happens. I did a project for one of the coal mines here in Colorado, or in Wyoming. And they wanted me to replace a piece of software that they hadn't been able to upgrade for a significant amount of time. In fact, this particular piece of software was running in a language called PHP 1.27. PHP, I think, is on version 8 today, and it's running on Windows XP. The last supported version of XP was about a decade ago. So, yeah, they kept installing patches and trying to figure out how to put in things like security patches on this, but they could not get those to work because whenever they put in a security patch, it broke their application. So they've been running this critical piece of infrastructure for decades on an operating system that is so old it isn't supported. And the reason is because they couldn't patch it, because every patch broke their application in some fashion. And they couldn't figure out how or why it broke it, so they just kept running it on the old OS without patching it. So, yeah, later you get a security patch, it's going to change something, it can break your application, you may have to go back to testing it again. So yeah, the tests become critically important for the long haul. Now, the test has gotten long enough that it isn't going to quite fit on the screen. And I'm actually going to go and add to it this missing case. The first thing we're going to do to work around it not fitting is, all of you have seen this routine quite enough. I'm going to scroll down to the test cases because that's the piece we're working on. So the function is still up there off the screen, but it's hidden. Okay, this is one of those things that I would say is a really, really common pattern for me to do testing. Is I start out with a variable set to 0. That's the number of failures I found as I'm going through a set of tests. And just start that out at 0. Every time I found a failure, I'm going to increment that value. Now remember that the assignment operator is not like equals in algebra, where the left is equal to the right. This would obviously be in algebra a false statement. Here we're taking the value that we calculate on this side, and error plus 1, and that's the input, calculating it, and then copying that value back into the same variable on that side. So you'll see that that's repeated, and there is some justification to not reusing code and typing things over and over again. When I do test cases, I want them to be simple, and by golly, if they simply string down the page, there's lots of page inside your files. There's plenty of room. So I tend to cut and paste, or I tend to have very simple tests that go through a simple set of input, one item at a time in an array or one set of items, and do the test over and over again. There is another kind of testing that we will get to about performance testing that has to do something else. But right now, this is the kind of test we're after. It's a functional test, a unit test. And I've still got, I'm going to call the function with -1. I'm going to check that I got the correct value 1 back. Same thing with 1, I get 3. With 10, I get 12. With 11, I'm hoping I just added this test that I get 55. Okay, we'll see. With 20, I get 55. In fact, anything else that's larger, I should get 55. So I should have covered all the possible cases. I already know that with this set of tests, that I have at least covered the code inside the function. I have covered reachability. Now, I've changed the printout statements. Instead of it just saying it failed, I'm real explicit that I expected 1 and I got this other value in each case. There are other things that you can do to help yourself with the testing, but if you at least print out, this is what it should have been, this is what I got, the instant you do that, you can look at it as a human being and say, well, this isn't that. Let me go find that test case and go find out why. And instead of focusing on, well, it's broken, suddenly you can focus in on, this test case failed to pass. And you've closed in on the surface area that you have to work on. You can start asking the questions of, why did this test not pass? And that closing in on what the problems are means you eliminate a whole world out there. You say now, okay, this one doesn't work. I'm going to fix this particular case to work. Then I'm going to rerun the test and make certain all the other cases still work, that I didn't break something. And that concept right there of being able to close in and work on a smaller and smaller and smaller problem, that's a productivity concept. That's something that makes you get through large pieces of code quicker and with fewer problems. Now you notice I did add this test case that I knew I was missing. So we've got it at every boundary value that should exist inside the function. And down here at the bottom, I've added another thing. It used to just print out pass, but now it says if the number of errors I've gotten is 0, that's equal to 0, then I print out pass. That means it didn't find any test case that failed. Else, I print out the number of tests that failed. So if one of them fails, it'll print out which thing failed and why. Then it'll go down at the bottom and say, you failed this many tests. So let's run this once and see what it prints out. I think the code probably works. And it prints out happiness. It prints out pass. It's like we did all this stuff and we reduced it down to one little fact. It passed. Okay. Now let's break it and see what happens. Let's do... let's break it. Okay, here's my code from before where I return a bad value. Uncomment that. And let's run it again and see what happens. And okay, instead of it just printing out fail, 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 it prints out fail. Expected 1 got this value. Okay? And at the bottom it prints out it failed to pass 5 tests. Now, the reason why you would want to print out how many tests it failed is if you get some big complicated piece of software, you may have thousands of tests. And you want to know how many of them failed. Okay? You want to be able to close in on, oh, I fixed something and I went from 5 failures to 4 failures out of 10,000 tests. That's an improvement. You're making progress. You're going in the right direction. If you go, oh, I've got 10,000 tests and I've got some failures somewhere, but I don't know how many. And you run it again and I don't know how many. You don't know if you're improving or getting worse. So that summation at the bottom that says that, yes, this is how many failed, that's an important piece of this. You see software, and I'm not kidding about the 10,000 tests. There's a piece of software that I use called Redis, and literally it runs through, I think, 11,200 tests. There's another piece of software that I use once in a while called SQLite, and it has over 100,000 test cases that it runs when you build the software. So, yeah, these things are realistic numbers, and I will guarantee to you in both cases, I have looked at the source code, there is way more code in the testing than there is in the code itself, because the testing is what makes it work. Now, in the land of software, the first thing you want to do is you want to make it work. Okay, then you want to make it fast. Okay, so the first question is, does it work? And unit testing will help you. All right, let's move on to the next thing. We're going to look at some other ways to use if, but this is a huge thing in terms of being able to close in on working code. Later in the semester, we're going to build this game. All the code is in the book, but you're going to type it in. You're going to make mistakes typing. And that's okay, because you get to test things. And as you're doing it, we will improve on our testing a little bit more so that you don't have to stick the tests in right with the code. But, when you do this and you start building, okay, this function does this, I've got a test for this, I've got a test for that. As you build tests, you take the entire big pile of code and you reduce it to, yeah, I've tested all of these pieces, I've gotten them to work. I've done this set of tests, I've seen this work. And some tests are not as easy to do as this because stuff doesn't return clean numeric values or things like that. For instance, at some point, the game is going to draw graphics. And it's not so easy to test the graphics to make certain that it's drawing the right graphics. But if you have tested 90% of it and that leaves you 10% where you've got to run it and see the graphics, it's a lot easier to know that, yeah, the problems have to be over here in the code because this is the piece that doesn't have these automated tests. All right, we'll catch you later.